Okay, I'll
So,
grab the screen.
yeah, our first speaker is Rich Pavlovich from UBC, and he will be talking about, as you can see, surface currents in and around an atoll in the South China Sea. So I will just let you begin when you're ready, Rich.
Okay, thanks. You can hear me? Yep.
Yep.
Okay. So there's an atoll in here. Beautiful picture. This atoll is right here, this little green dot on the Google Maps in the South China Sea in here. It's a little tiny circular atoll that's administered by Taiwan from over here um, as a national marine park, but it's claimed by the People's Republic in here, and there's, I guess they claim everything around here, but there's all kinds of military stuff going on there. But biologically, it's actually very interesting. There's a lot of papers about this atoll. From the physics point of view, not so much, but the big interest in this area is over here in the Luzon Strait. When the tides go over these sills, you generate these world's largest nonlinear internal waves, which then kind of go westwards and splash against the shelf and Dongsha Atoll over here. Okay, and so some little facts about it. Here's this picture again. It's about 20 kilometers across in here. In the middle, this blue section is on the order of 15 meters deep in here, but you see all these little specks everywhere. These little specks are these knobs of coral that come up to or even just below the surface, and so getting a boat in here is a bit risky because everywhere you go, you can run into something in here. Outside, it's kind of 300 meters deep, so it's like this big cylinder that's almost filled up in here. This island on the west is above sea level. There's an airport here and soldiers and a research station. Um, and then there are these sort of deeper channels, about 6 meters deep on either side of it. This whole area around here is the reef, and although it looks like it's dry, in fact, it's just about underwater most of the time in here. You can see this white stuff along here is where waves are breaking because it gets pretty shallow at the spring tides. Yeah, the tides here are about a meter, and at spring tides, some parts of it are perhaps dry, but otherwise it's awash, and people go in here to illegally fish and so on. And so when I learned about this during a visit to Taiwan a couple of years ago, I was immediately interested in the question of, what is the circulation inside here, and how does exchange work between the atoll and the water outside in here? And for a number of years, I've been playing around with Lagrangian measurements of ocean circulation with these expendable drifters. Here's a little picture, right? There's a GPS tracker and a satellite unit, and $25 worth of wooden roofing flashing in here, which will give you positions every 10 minutes for about 4 weeks. And I have, thousands of days of this stuff. Here's a sort of a picture of what we have in the Salish Sea. So I persuaded my collaborator there to build a few of these and ship them out. And in May 2019, we deployed 9 of these. The original idea was to put them all out inside the atoll itself in here and see what happened to them. Some of them went inside, some of them were deployed outside. I guess, the boats tend to go around the outside rather than the inside because of those knobs. And well, you can see they kind of did all this stuff and eventually drifted off, making little loopy things off to the west and north. Okay, so what do we learn about this? First thing is looking inside. Here's another satellite picture with the tracks on the inside, and there's no particular pattern that you can see here, no nice sort of in and out or anything else like that. The little dots are the actual positions, and one thing you can see is that inside everything is a lot slower than outside, right? These dots are kind of spaced much further apart outside, and so if you do a histogram of it, you find that inside the speeds are I mean, the average is 9 centimeters a second, but the peak is a little lower than that, whereas outside it's kind of half a meter a second, so considerably more than that. And I didn't really know what to make of this until at some point I kind of realized that they often were moving in a downwind direction. And so if you sort of do the ratio of the speeds to the wind speed on top, what you find is that in the downwind direction, you're moving at about 1% and across wind nothing. And so right away, the sort of conclusion is the downwind speeds are about 1% of the wind speed in here. I thought, okay, there's slight evidence of a tidal oscillation in there as well, and a larger one, these little wiggles, which we'll come back to on the reef as well. But inside here, 1% of wind speed. And so I thought, oh, it's, some kind of frictional control of what's happening inside here. However, 1% is sort of a funny number for those of you who have looked at drifters. In the year after that, I took part in this thing called the tracer release experiment in the St. Lawrence in here, and the part that I was particularly interested in is we put out 7 different surface drifter designs plus rhodomine dye to see what wind driving really means, right? The idea was to put the dye out. Here's the picture of the dye after a few hours, and the drifters in the middle to see if the dye stayed with the drifters. Here's a picture of all these different designs, and a summary of that is here I've plotted the position of those drifters relative to the dye, and you can see that pretty much instantly they moved kind of downwind of the dye at rates of anywhere from 1 to 4.5% of the wind speed. And my design, the one we just used, appears to move away from the dye at 1% of the wind speed, partly from Stokes drift, partly from wind drag on the water, and partly from wind drag on the drifter body. And so this 1% of the wind speed in Dongsha Atoll probably doesn't mean anything, and the currents in there are even weaker than that. So I don't know if that was disappointing or not, but that's what it was. On the other hand, on the edges of the atoll, here we've got one drifter came along and then went across and then did this sloshes back and forth here for a number of days. And if you look at this plot over here, you can see this is sort of radial distance from the center, okay, in and out, and I've plotted the tidal height there as well at the same time. And you can see that everything clearly looks linked to the tide in here. And yet, if you color sort of falling tide by green and rising by red, which we've done here, you sort of think, oh, falling tide, this should all be green and this should all be red and green and red, and doesn't exactly match up that way in here. So there's some tidal signal here. It's pretty big, right? Speeds of 10, 20 centimeters a second in here in water, possibly not more than a couple of meters deep in here, but quite delayed. And so to look at that, I played around with a fully nonlinear shallow water model with the kind of wetting at the eastern reef in here. And so here's sort of a cross section, and then I ran the tide up and down, so the water level went up and down. Here's sort of an example when it's falling, and you can see because of friction, there's a bit of a hydraulic control at this side and maybe a smaller one at this side in here. But the upshot of that is if you look at the phase of this is tidal height, you can see there's definitely a phase lag from the inside relative to the outside. And even over the reef in here, if you look at this area, things can become much more complicated. So that was kind of interesting. And then outside the atoll here, so we had lots of these long loopy inertial things, which you always see in the open ocean. But this is a satellite picture of the atoll and the surrounding waters from Sentinel-2. And what you really see are these huge ripple patterns, which are clearly these large and nonlinear internal waves that are coming from the Luzon Strait that are coming along. And look, here's a little reflection as it's splashing off this cylindrical atoll. Here's a sort of an analytical picture of waves scattering from a cylinder, and you can see how similar this is, right, with a little diffraction behind it and everything else in there. But one of the problems about looking at these internal waves is that the overpasses are only every 5 days, and it's cloudy a lot of those too, so you don't get too many pictures like this. But one thing I did notice is that when you looked at the drifters outside, here's a track of the drifter, and this sort of looks kind of normal, but if we look at this particular place right here, okay, here's the drifter moving along, and then it kind of, when we go past this corner, you get this thing, but you'll notice there are these little wiggles in the path. And if you actually take the derivative of this to get velocities, you see this green pattern, which looks a lot like the signal you would see from a nonlinear wave packet in here, right? Like it's just the sort of same ripple patterns you have here. And in fact, this stuff occurs about 5 hours after, sorry, this was 5 hours before the time of this image in here. And so if you measure this distance, okay, you get a speed of about 1.7 meters a second, and you can see that these oscillations of amplitude are almost a meter a second in here. And over here's another example. This particular drifter was going along here, and then about 2 hours after this image, we see that same thing with the velocities over in here. And so these jerks, and there are actually quite a number of examples of this in the drifter tracks. But clearly, we're observing the nonlinear internal waves with surface drifters here. And not only by comparing with the image can we get some idea of propagation speed, but we can also get the nonlinearity in here by comparing the speed anomalies within the waves with the propagation speed. So surface drifters can be used to observe internal waves, which I think is pretty cool. Okay, so I guess that's the summary here. Is we learned lots of interesting stuff. We still don't know the circulation and the residence time of the atoll in here, so there's more work to do, but a very fascinating place to look at surface currents. Thanks.
Thank you very much, Rich. I was just going to give you the 1 minute warning, but you're right on time. Yeah, that was very, very cool. Are there any questions or comments from the audience? Oh, Cedric has his hand up. Cedric.
Hi, Rich. Can you hear me?
Yep.
Very nice. What's the period of the internal waves that you measure with your surface drifters?
Let's just go back here. I think you can tell that these like these dots are 10 minutes apart, right? So this is sort of 20 minutes roughly. So the 10-minute sampling is maybe, it would be better if we had 5 minutes sampling to see this. I think we're still not quite getting the full, the full pattern with these.
Okay, but yeah, it's nice that even with 10 minutes, you can see those things.
Yeah, I think in in something like the St. Lawrence, we would have to go down to 2.5 minutes or even less to see this, though.
Yeah. Another quick question. You showed on the first picture, you had some streaks, and you had the question, what are these?
Oh, yeah.
What do you think they are?
I don't know. Actually, I put this on here just in case someone would ask, but a number of so we looked through several years of these daily images from Planet in here, and a fair percentage of them in the summer show these little streaks coming off from the eastern side of the atoll in here. And so I suspect they could be some kind of oil that the reef organisms are exuding during the summer in here. And then you've got these, maybe it's this Langmuir circulation gathering it in these long lines going downstream. But, in the scale, right? I mean, this is kind of 5 to 7 kilometers in here. So it sort of seems a little, a little unlikely somehow that they're related to Langmuir circulation alone. So it's a mystery.
Okay.
Open to suggestions, really.
Rich, I have one question that's about the atoll. Did you look into, because with the phasing difference, did you look into any sort of resonance, like a Helmholtz type resonance, like you'd have with a bottle?
Sorry, where was it here? Yeah, I guess I didn't. So one of the if we go back to this, it's the original picture, right? I mean, if this was all closed off and you really had stuff coming in and out here, then that would be something to look at for sure. But given the fact that water is going back and forth everywhere along here, I guess I'm not quite sure how that would work or even how I would model that exactly. So starting with a 2D model is something you can do pretty easily, and the friction people have done looked at the sort of the flow round atolls in here in this way, and friction does seem to be kind of important. So I think I'm going to lean towards that right now.
Thank you very much. There's one question in the chat. Maybe, yeah, Mike Casey. Maybe you can ask that quickly, and we'll get to the next presenter.
Yeah, I can see that. Any trouble with the drifters running afoul of the reefs in here from Mike Casey? Let's see. When you look really closely at it, there are a couple of times here when we're getting close to some of these knobs in the middle. And for example, this track along here seems very close to where things are getting shallow. And although you can't tell on here, actually even on this one, I didn't mention this, but on this radial distance, with time, you can see there are places here where we've actually run aground for sections of time. It's sort of not obvious here, but they certainly are running aground while the tide's kind of low and then getting picked up again. So I guess the answer is yes, it is happening.
Thank you very much. We should move on to the next presenter.
Thank you.
Yeah.
All right, so our next presenter is Koshen Chung. Koshen, if you want to try to share your screen. Great, so we can see it well. Thank you very much. Yeah, so Koshen will be talking to us about an operational drift prediction for shipping containers. And we can't hear you. I don't know if your mic is muted.
All right, thank you, Nancy. Thank you, Greg.
Perfect.
All right, so my name is Koshen. Early last week at CMOS, we all learned about the impact of atmospheric river on our daily life. The Dim Kingston instance is one of the examples. So our section, Environmental Emergency Response section, finished the working prototype to deal with this type of instance just 1 week before the Dim Kingston. We were not sure when we need to use our tool, but we did this case to validate our model. So let's dive in. Next slide. Yeah, it's not moving. All right. So on October 22nd, 2021, the Coast Guard reported there were 40 containers overboard due to the severe weather. It was 160 kilometers per hour in gust and over 5 meters in wave height. So just imagine that scene when the vessel jetted back and forth until 35 degrees. So in the first week, NSP was not able to arrange the flight, and later on, there were 109 containers reported overboard, and only 4 containers were found on shore. So this tells us the emergency drifting simulation could be very useful to support the search and rescue. And we found that there was not a lot of information to set up the simulation, and the situation of the drifting was constantly updated. So the most thing for us was that we need a tool to respond quickly and accurately for this type of instance. So our objective is to develop and validate an operational tool for emergency response that object is moving by itself or drifting at waters. Last year, we introduced the advanced nonlinear source term for stationary instance, and this year we focus on the source term for non-stationary instance. This is one of the containers overboard from Dim Kingston, 140 feet containers, roughly about 40% of the body is under the water. And this one is 3 containers interlocked. About 70% of the body is under the water, and you can see one of the door is wide open. This is another object with 5 containers bundled together, roughly let's say 50% of the body is under the water. So you can picture that we have to deal with the great uncertainty in terms of determining the leeway objects and its associated leeway parameters. This is one of the grounded containers. It was smashed on shore, surrounding by the debris. So today we are going to talk about a tool that we use to track the containers from Zim Kingston, and the tool is called MLDP. MLDP is the Lagrangian model we developed at our section and has been used for many emergencies. So to achieve our goal, we need to work on majorly on the interface for responders, the source-term modules to see the particles, and the kernel for the leeway kernels. Speaking of leeway kernels in MLDP, we have to upgrade and move from the Kansas 3-parameter leeway to US Coast Guard 9-parameter leeway. And we follow the similar algorithm in OpenDrift to construct our kernel in C programming language. We validate our kernel with a series of cases from a very small object like person in water to a very large object like bulk carriers. Here is the workflow in our leeway kernel. 3 major components over here. The first part is the US Coast Guard leeway table, and the middle part is the OpenDrift algorithm, and then we move the particle within our MLDP. This is our operational user interface. Basically, there's 2 options we designed to achieve to activate the simulation. Option 1, just select the object names from the database, and option 2, run the leeway with the customer entries. So just with a few clicks, the responder can get the job done. One thing we like to highlight here is the implementation behind this interface. The first, we provide a guideline and SOP training and exercises with our responders at ERS. And second, we keep validating the tools with the measurements from our clients. And third, throughout those validations, we expand our database for next time operational preparation. For the Zim Kingston case, we configure the model with our best available operational forecast at CMC. For material, we use the HRDPS. For current CMOS. In order to understand the effect of the wave model on leeway simulation, we tested the regional wave model. This is the process domain, about 1,500 kilometer coastline feature was processed at the 200-meter resolution. As you can see, there was very strong current moving along the coast to north at 1 meter per second. On your right, you can see the regional wave model showing a significant wave height over 7 meters. This illustration above give you an idea when the wave height is included in the calculation. The particle can move faster due to the stock drift. This is the simulation showing the two trajectories. The fast track is the simulation with the wave model. The slow track is the without the wave model. So by comparing the observation, the leeway simulation with the stock drift has a better agreement with observations, and it touched down to the location where the container was found on shore. This simulation indicates that this is necessary to include the wave height in a leeway simulation, particularly for the severe ocean condition with the significant wave height. We compare our model results with the current operational model oil map side by side. You can see our model produced a very similar drifting 5 days simulation. And this demonstrates that our model produced the reliable results with the best available forecast right on site at CMC. Let's recall some pictures we saw in the beginning. The biggest problem is that we have still with the uncertainty of the drifting objects condition. Several studies already shown that the immersion level is an important factor for modeling drifting containers, and then it varies by cases. To resolve this problem, we follow the same method that MOSI, the operational model, applied it in France. It applied this function to scale up the leeway rate at different immersion levels. If I apply the function and you apply that, you can get this figure on your right. Also, by following the same method, we expand our leeway table just based on the 140 feet container in original leeway table to the objects with the multiple with the different immersion levels. So here's a quick leeway assessment with the various immersion levels. Two grounded containers are found over here, and then the other two are found in the north of the Vancouver Island. So clearly, the one single leeway object definitely is not enough when dealing with the instant with when the drifting object condition is greatly unknown. And therefore we recommend that this is necessary to conduct a quick assessment with the different emergence labels to exempt the possibilities due to the drifting uncertainties. We management to get this done very quick in 10 seconds with 1,000 particle per trajectory. So in operational time is not always your best friend, so that helps. In order to communicate with the clients, we propose two products. This one is the trajectory to show the general movements, and the little red dots are the mean particle location at each time step. And then the next, the other product is the probability, which is based on the particle count per model free cell, the NBC on your left. So if you compare the left and right, the NBC and the PROV, you can see the PROV now is much cleaner and sleeker and more precise to just pinpoint to indicate where to retrieve those the lost items, and then for the application of search and rescue. So you might wonder, hey, can we respond to much larger items rather than 40 feet containers? This is the 200-meter bulk carrier Alan drifting in 2019. The main engine stopped after the fuel swap. The ocean was calm. This picture shows you that two top boats are leading the Alan heading to Vancouver. The top ETA is 48 hours. So that means that tells us we need to have 2 to 3 days of forecast capacity. This is the 41 hours forecast with HRDPS and web type. The yellow dots are the reported positions, and we did not fit the leeway parameter. And this result is just straight out from the first simulation. Our model shows very good agreement with observations in this case, and in general for this case, the model errors are within 10 kilometers. The take-home message is that we proposed SOP to deal with the situation when the leeway object is not listed in the leeway database. In conclusion, we developed a tool based on the US Coast Guard leeway table and the OpenDrift algorithm to respond to the drifting instance. And we have validated our tool with a series of inventory instances, and also proposed SOP for our responders. We keep validating our kernels and with the incoming data set from our clients, and also take a chance to expand our leeway database. And we based on the suggestion from our clients to design the interface and products. And we, as you can see, we can take on this and to develop our capacity to respond oil spill instance causing from the drifting or the mobile sources. So the source code can be found in our EC GitLab repository. So you can take a look for the kernel, the interface, the products. And if you have any question, please contact me or contact Paul at ERS. And thank you so much for today. I'm here to answer your questions. Thank you.
Great, thank you so much, Koshan.
Yes.
Do we have any questions?
Yes.
Koshan, I have a quick question.
Yes.
You presented some information about our table with the leeway parameters for different types of objects. I'm wondering if you could comment on how those leeway parameters are determined.
All right. So are you talking about the this slide?
So I think at one of your slides you had a table with a whole bunch of different leeway parameters.
Oh, this one?
No. It was, I think, maybe I'm misremembering, but I think it was a slide with a some of the user interface through MLDP or the SPI program.
This one? With the side-by-side comparison with all map?
No, okay. I mean, so I guess what I'm asking is that the results of your simulations depend on leeway parameters for different objects, classifications of objects, right? So I'm wondering how, if you could share how those leeway parameters are determined for the different object classifications.
Yeah. So basically, for the containers, we really don't have they did not let us know the dripping conditions. So in our exercise, I think we explain, like I say, based on the method that applied in the MOSI. So we scale up and to create a multiple of the DA object, and based on the emergent label, just based on the equation, and then we scale up based on the equations, but from here, from the screen, you see this one. For this one is much better. Is we did not adjust the additional adjust the DA parameter, so it just include a weight, and then you compare all map is quite nicely have an agreement. But to here, I did not know how the DA parameter used in the oil map, but I do know the weight pi to be included in our simulation. And if you take one step forward, is when the DA was not determined, or when the DA parameter is not be found for the interest object on the leeway table. So that is something you have to by compare the object the geometry, and then you see like a similar object, and then you kind of by your mindset you think, okay, like geometry is similar, and however the size is different. So start from there, you select the object from the leeway table, and then with the similar geometry, and then you scale up from that. So let's give you the idea how to set a parameter from the existing US Coast Guard leeway table. And normally, when just in the instant, it usually have every 4 hours, they request the ship owner to report a GPS location. So that means when we simulate the first report, and a couple hours later, it's going to have one observation coming in. So it takes the time to update, to adjust your first parameter you set for the first simulation, and you calibrate, adjust, and then for the second run, and you're going to get a much better result. But it kind of, have a good, every 4 hours, every few hours, observation. That's the opportunity to adjust the DOA table, to adjust the DOA parameter. Okay.
So thank you. Thanks, Koshan. Yeah.
Nancy, maybe I can help to answer the question, Nancy. I think.
Sure.
Yeah. So Koshan, I think the question was that how are the different parameters given? Okay, how they assign for those different objects, and it comes from a linear regression, right?
Oh yes.
I mean, correct me if I'm wrong, but I mean, this comes from empirical data.
Yeah.
Okay, and they're linear. So all those parameters are actually come from the linear regressions okay, for different objects subjected to different winds.
Yeah,
Okay.
yeah. Thank you. As the
All right. Thanks,
US
Paul
host.
and
Yeah.
Koshin. Yeah.
Thank you guys very much. We should
Okay, I think we have to
move.
move on.
All right.
Yeah.
Thank you.
So our next speaker, thank you all for that, is Donovan Allam from the University of Waterloo. He's going to be talking about finite scale Lyapunov exponents, but the assessment of drift prediction in the ocean models using finite scale Lyapunov exponents. So, are you here, Donovan?
Oh, I had myself muted.
Oh, yes.
I fixed that.
Okay. There
Can you hear me now?
Yes.
Okay,
So
I think
Koshin,
yeah, is still sharing a screen.
yeah, you need to, yeah. If you can stop sharing your screen, please, Koshin.
Oh, okay. Oh, sorry. Is that
No problem.
stop?
It's a button at the top of the screen, I believe. Oh, there
All
we go.
right.
Yeah. Okay.
Excellent. Thank you. All right. All right. And everyone can see my screen just fine?
Not yet.
Okay, my computer's a little
can't yet.
slow. So okay. So just give it a moment while it goes full screen.
Oh, yes. Here we are. I can see it now.
Okay. Looks a little. There we go. Well, wrong slide. There we go.
All right.
Okay.
So thank you very much. Yeah, start when you're ready.
Okay, sounds fantastic. Okay. All right, everyone. Hi, I'm Donovan. I'm here to talk about a study of drift and dispersion in the St. Lawrence Estuary, and what we'll be talking about is a particular measure called the finite scale Lyapunov exponent. I worked on this project along with the collaborators listed here, Nancy and Greg, who are here, as well as Mark Stasna, who's my supervisor, and Christopher Subich and Simon Seythal-Drouin, who also work for similar departments at the Government of Canada. I also want to thank the Réseau Québec Maritime and Miopar, who provided funding for this, that made this research possible. All right, so there's really two parts to the talk. The first part is what is it? So we're talking about this quantity that some of you I'm sure are familiar with, but some of you may not be, the finite scale Lyapunov exponent. And so first, what I'm going to say is, what is the Lyapunov exponent? The second part of that big word there, that big phrase, and then I'm going to talk about what the finite scale part means and what it contributes to this concept. And then in part two, I want to discuss the data that we use for this, using this measure that we want to apply the measure to, and then I'm going to compare the result, the measure, the calculation of this measure between the drifter data as well as modeled drifters as well. Okay, so part one. All right. So what is a Lyapunov exponent? So the Lyapunov exponent is obtained, and we can talk about it using this picture here. So first we have a particle trajectory that's determined in time by this function x, and we also have a nearby particle trajectory. So another particle also drifting, and it's the same function, but it's slightly different by some amount delta. And then we have some initial separation at 0. So what this is saying here is that initially they're very close together. These are all infinitesimal time scales and length scales here. And if you make a sort of a linearization and assume everything is infinitesimal, then it can be shown that the separation at a later time is equal to the separation earlier multiplied by this e to the power of lambda times t, where the lambda there is the exponential separation rate, otherwise known as the Lyapunov exponent. And the Lyapunov exponent is often used to describe chaotic systems, and it's usually discussed on infinitesimal length and time scales. Okay, so that's what the Lyapunov exponent is. And so the question is, what is the finite scale Lyapunov exponent? And the simple answer is that it is a finite scale analogy for finite scale perturbations. So now we're going to be talking about finite. We're going to try and use this quantity to define a equivalent finite measure. Okay, so we're going to start with, I'm going to derive it, and then I'm going to sort of show you pictographically what it really means and how we can calculate it. And so there's only one in the infinitesimal. There's only one. Well, there's actually many Lyapunov exponents. but there's only one largest one, which is often what is talked about in that context. But we can let's talk about it over the infinitesimal. So we can start with this infinitesimal equation. I'm going to solve it for lambda. So you don't need to really think too much about that, but I've just rearranged this equation assuming the equal sign is true. And I've also rewritten some of the variables. So we have delta, a change in time rather than 0 to t, but everything else is the same. And so this is the equation we're going to use to calculate the finite scale Lyapunov exponent. So let me explain sort of how that is done. So we start with a pair of distances, d0, which is the initial separation of two particle pairs. So we have a particle pair here. And then we have d1, which is some later larger separation distance that they might reach. For all we know, maybe these particle pairs are caught in an eddy and then run aground before they reach this larger separation distance. But we're going to assume for this argument that they do. And if you know the time, if you have the data about the particles, then you can determine the time it takes for the particle pairs to separate from d0 to d1. And as a result, using this equation in the top right, you can calculate what we call the finite scale Lyapunov exponent for this length scale. And we can repeat this. We can choose another larger distance, d2, and we can, if we know the time it takes for the particle pairs to separate, to increase their separation distance from d1 to d2, then we can define a different Lyapunov exponent for a different length scale. And you might notice that the distances between these points are different. They're not fixed, and that's intentional. It turns out that what we do for this project, for this quantity, is we keep the ratio between subsequent larger distances fixed to some scale factor r that we choose, and it's sort of a trial and error thing. And we can repeat this process starting from some initial separation d0 up to whatever separation is relevant for your calculations. And so you can have a different sort of effective exponential separation rate for each of these scales. And we use this sort of increasing bin length. And the reason we use them is because if you have pure exponential separation, then the Lyapunov exponents will be constant regardless of scale. So they'll just be constant. And so we can kind of think of this quantity as you can think of it compared to an exponential separation. So here's the total definition here. We have on the right each of the distances that are chosen, and then on the left what we have is the Lyapunov exponent defined by the logarithm of the scale factor r divided by the average time it takes to get to distance I to distance I plus 1. And so we take the average of those, and that's how we get the Lyapunov exponent. So in the previous page, I was talking about a single particle pair. Well, really, you're talking about many averages of many. And at the bottom, we have just the values we chose for this project, which again, we chose them mostly through trial and error and a bit from informing from similar papers and stuff like that. So that's what we got to. Okay, and I want to briefly discuss, this is an important part of using the FSLE is its relationship, and it's sort of hand wavy as a mathematician, it's hand wavy, a relationship with the relative dispersion. So relative dispersion is a the average of the squared separation distance between particle pairs, and it's averaging distances at fixed times, whereas the finite scale Lyapunov exponent is averaging times at fixed distances. So that's the sort of distinction between these two. They're very different, but they can be compared. And typically, in fact, this is used several times in the literature, and I think in at least one location I'm aware of that it proves actually sort of accurate. But it is very hand wavy, and it's often you can think of it like this: is that if the relative dispersion obeys this power law, then it can be shown. You don't really have to follow these steps. Really, the final step is the one that matters. That the FSLE also obeys a power law, but instead of in time, it's in terms of distance, the length scale that you're talking about. So that's a very useful tool, is that one could think about it calculating the FSLE instead of the relative dispersion if what you were after was determining the dispersion regimes. Okay, part 2. All right, so the basic research statement is we want to study drift and dispersion in the St. Lawrence Estuary using the finite scale Lyapunov exponent. And the estuary is nice in that big red circle there. Funnily enough, I actually be within 20 meters right now of the St. Lawrence River. So I'm not quite in the estuary, but I'm pretty close. So that's the main area that we're concerned with. And on the left, we have some average sea surface currents from one of the models we'll be considering and comparing with. We don't use the average currents for our calculations, but these are useful to see sort of the development and the different sort of features that are present. All right, so the data we used. Rich already mentioned these. It's from the 2020 tracer release experiment, T-Rex, and I'm just concerned with the drifters themselves, not the dye. And just a summary is that over 200 drifters were released in the estuary near Rimouski in that red circle there. And they returned their position versus time data, and that's what we have. That's what I'm showing here on the right. It's all of the different paths. And we're going to compare these drifters to equivalent model drifters that are released from the exact same location from two models that are currently in use by the government of Canada, and that's the Gulf of St. Lawrence model, and then also the CEOPS East model, the eastern domain of the coastal ice ocean prediction system. So we'll have we have drifter pairs from the observations, and we have these model equivalents, and we can calculate the FSLE separately and then compare the results. And this is our comparison. This is the main result that we have. And before we talk about the results themselves, I just want to mention that we're looking at a log-log graph here. So this is good because power laws, like t to the power of alpha or d to the power of some constant, are straight lines on log-log scales. So these are useful because a straight line defines typically a dispersion regime, or rather power laws define dispersion regimes. And so you can think of seeing straight sections as dispersion regimes. It's a bit hand wavy, but that is sort of a way you can think of using it. All right, let's look at the observations first. So the main point here, it's consistent shape over all length scales. So if we're using the sort of dispersion regime framework, and really it does, indeed, if there is a straight section, it defines a different, it could be modeled by a different power law. And there's no evidence, there's very little evidence of changes in shape throughout this curve, which is surprising because we're talking about 0.1 kilometers to 100 kilometers. That's the range we're looking at here. And if it turns out that what this sort of suggesting is that that in this estuary, for those drifter paths we looked at, in the FSLE, there isn't the appearance of some sort of change associated with the estuary width or the size of the large eddies from the gas bay current or any sort of other circulation. It seems consistent, which is a surprising result. But it is quite robust, and you can, if you squint hard enough, you can actually see the confidence interval, 90% bootstrap confidence interval, that shows that we're pretty confident in this being the correct answer. At least the average is in this range there. And then we have our models, the two models here, the curve, the FSLE from them. You can see there's a vertical offset, but I won't get too much into that. And then that is likely due to the different resolution of the models, but although we haven't confirmed that. So the difference is that there's shallow slopes, much shallower slopes at small length scales, as well as the magnitude of the FSLE smaller. So that suggests that generally in the models, the drifters are separating on these really small length scales much slower than the observation. And so that is an important point for people, particularly in search and rescues, who may be using these models to predict these events. And then there's a convergence to observations at large scales. These are in the circles that we see that I've added here. And the GSL model converges at a smaller length scale than the CEOPS East model. That's not particularly surprising. It is the higher resolution model, about 5 times. But some of you who are in the know would know that the CEOPS East model doesn't really have square grid boxes, but generally it's about 5 times, somewhere in that range. And so it's not surprising to see that the GSL model would converge at a smaller length scale. And it doesn't completely converge, as you can see. Like it is imperfect. There is this dip at 65 kilometers, which we could look further into in the future. Now the focus of our paper is more on the small scales incorrect, big scales correct, or at least closer to correct. And so that's the main observation we see here. So for someone, really what we're seeing here is that the models at small length scales are systematically underestimating the separation rates at small length scales.
1 minute, Donovan.
Okay, thank you. Okay, so the FSLE. So really what we got out of this project and this research, we assessed this measure, which has been mostly used in open oceans. And what we have is a relatively simple and robust calculation. And we can, you can get that out of the confidence interval alone. We're quite confident it's robust, at least. We threw some drifters off into the ocean, into the estuary, and it worked pretty well. And it provides a potentially useful comparison along with other measures between models and observations. The downside, of course, is that it's based on an average, and in our forthcoming paper, and I don't have time to talk about it today, we have some additional measures that go into opening up past the average and looking at the exit times themselves. And these are right here we have some of the main references we used. And thank you everyone for listening. That's the end. Thanks.
Thank you very much, Donovan. So we have time for one question, and I see Susan Ellen has put something in the chat. I'll just read it out if you don't mind, Susan. So it says, did you include any subgrid scale randomness for the model trackers, i.e. the Eddy diffusivity?
We did at some point have, we tried looking at just Brownian motion. We added some to the drifters, and it didn't fix the problem. It didn't fix the difference, but it did actually increase the FSLE. And what I mean by it didn't fix it is that it didn't correct the slopes. It just, if you increased the value, it just increased the uptick at small length scales, particularly focused on the small length scales. It had no effect at large length scales, as one might expect. It increased the magnitude and the slope, and but it never really matched. We couldn't. I mean, it's a little bit. I'd call it a little bit hand wavy. But if there was a nominal value where it would match it, we couldn't find one. It didn't appear to be that there was. If we just lowered it a little bit, okay, that would have worked. So it did affect the small length scales, and it pronouncedly dramatically increased the magnitude of the FSLE, but it didn't correct at least the slopes, which is what we would have liked to see both to work towards. Yeah.
All right.
Okay.
Fantastic.
Yeah. All right. Thanks a lot, Donovan. We'll move on now to our next presentation, which is indeed a poster presentation by Greg Sutherland. So yeah, Greg will be presenting on surface drift and dispersion in the Lagrangian channel during Hurricane Dorian.
Yeah, a poster introduction. So I will share my screen. Go to the first slide. All right, this will be quick because there's a poster on it for yeah, I guess I'll be hanging out in Gathertown later on. This is very preliminary work of some drifters some drifter data that someone provided for me on like the Lagrangian channel. I don't know if this is clear. So the color scales aren't the same. They're just really for a demonstration. But there was these 10 Oscar drifters that were deployed in September 2019. And if you see on the left track, there's this one line. This is the Hurricane Dorian track. And then we have these 10 drifters, and there's sort of two groups of 5. And you can see they mostly stay together. The hurricane passes around the 9th of September. So it's going quick. Hurricane, cold wave. And you see some like kind of large excursions there. And one drifter gets in a different system altogether. And then the rest sort of do their kind of drifter thing going eastward. And so I would like to try and look at sort of dispersion of this. So let's next slide. So I'm going to look a little bit at the diffusivity of, I'm going to use look at absolute dispersion. So this sort of contrary to what like Donovan was talking about, relative dispersion, how like the particles sort of spread out from each other. I'm going to look into an absolute where I can now calculate a tensor. So this has the problem where I need to know what like the mean flow is. And this is the huge uncertainty in this. So this is all very preliminary, but I will, I have a poster on it. So if you want to discuss, I encourage you to come find me. So just like the overview of like diffusivity, if I have, yeah, I'll have just a minute to go through this quickly. So I need a mean and a diffusive part. And so then the diffusivity will be, I can have now a tensor, like so at the velocity variance, and then like the distance from the mean track. And so this can be broken down into a symmetric and anti-symmetric component. So the anti-symmetric is non-diffusive, so it doesn't contribute to the diffusivity. And so then the symmetric part can be diagonalized. I have these two eigenvalues. Just as a little preview, this dashed line is the Hurricane Dorian. And then the one eigenvalue is always positive. So it's always sort of stretching in one direction. And the other one seems always negative. So it's always getting stretch and thin, like a filament. And then I sort of look a little bit at some like some quantitative values of this. Yeah, and that's it. So find me at the poster session. I'm happy to talk about this later on. And I think also in the interest of time, we will reserve questions and for that, unless there's something in here. No. So it's
okay, thank you, Greg. Are you finished your presentation?
Yes.
Yeah, okay. Yeah, so we are a little bit, we do have to move on to the next presentation. So I encourage everyone to find Greg in the poster session if you have any questions on that work.
Yes, so our next speaker is, it's Annika Tendeshat. I see that she is on the call. She is somewhere in the Labrador Sea.
Hello.
Aboard the Celtic Explorer. Are you able
can you
to
hear
share?
me? Does this?
Yes, it sounds really good.
I can try, but I'm afraid that's going to go at the cost of the voice because our connection is working at the moment, but I won't say it's strong.
Okay,
So,
well, I am happy to share the slides that you sent me.
Great.
If that's easier. Okay, so I will.
Yeah, I think that's easier.
That
you can hear me okay, right? There's probably a bit of a delay, but probably not too bad.
Yeah, let me just so share screen. Share. Okay, so is that clear?
Yeah, I can see it.
Okay. If it's tough, you can follow along on your own computer, and I can just slide along as you request.
Yeah, I'll ask a request, and I have them open here on my own computer as well, so it's no problem at all. You can just make it bigger, and I'll turn off my video just in case the connection falls back. But it seems all to work fine now. Thank you very much.
Okay. Okay. Yeah. Start when you're.
Okay. Second, let's see. Here we go. Okay. Hello. My name is Anneke ten Doesgaten, and I'm a postdoc at Dalhousie University. I'll present some work, the preliminary results of a research project that I'm working on with advice from Ruth Musgrave, Greg Sutherland, and Daniel Bourgault. This work was supported with a 6-month grant from MEOPAR, and it contributes to the trace release experiment in the Gulf of St. Lawrence, which you've heard a little bit about already. Yeah, you can move on to the next slide. The goal of this project was to set up, of my research project, to set up a simulation of turbulent dynamics in the ocean surface boundary layer, and use these simulations to predict sort of statistics of dispersion of material released at the surface. To achieve this, we've been trying out the capabilities of a recent numerical simulation package, which is called oceananigans.jl. It's written in the Julia programming language. This package is developed and maintained by researchers at MIT, and it's designed, supposed to make high-resolution simulations accessible to students and first-time programmers, which I would consider myself to be.
Sorry, Annika, I made a mistake here. Let me just start again. I think that was my problem. All right. All right, so can now people see the presentation?
Yeah.
Okay. All right. My apologies for that. So yeah, I'll just go to the slide number 2. I think it's where you were. So on goals.
Yeah, I kind of talked about this one. So this is just introduction slide. So here you see on the right a screenshot of a paper published in Journal of Open Source Software a few years ago, which is a brief introduction into the software package, oceananigans.jl. But yeah, you can go on to the next slide, please. Thank you.
Yes, you're there.
Okay, so the framework in which are we setting up this model is the tracer release experiment in the, or short TRX in the Gulf of St. Lawrence. In both 2020 and 2021, research campaigns took place in the lower St. Lawrence estuary over the section near Rimouski and a few kilometers upstream. During these experiments, a whole plethora of observations were made from the research vessel Coriolis and 2 small boats, drifting platforms, high frequency radar from the shore, drones, wave buoys and weather stations. Lots of observations were obtained. And as Donovan already showed, different types of surface drifters were released, and a dye tracer experiment was performed in these experiments as well. Yeah, next slide.
Okay.
So, oh, thank you.
Yeah.
The model I've been working on is set up in Oceanagans. It uses a 3-dimensional spatial domain with periodic horizontal boundaries and bounded in the vertical. The model resolves the Lagrangian mean velocities on a staggered grid. It resolves those, and it solves the wave average Boussinesq equations using the Craig-Leibowitz approximation. This means that not the instantaneous effect of waves is represented, but the phase average effect of surface gravity waves that contributes to the momentum budget is included in the equations. So the RC momentum flux consists of the combined effect of wind-induced surface stress and wave-induced Stokes drift velocity. Currently, the surface Stokes drift profile that's represented in the model, it represents only monochromatic wave fields, but it can be made time variable, as is shown here on the little sketch on the right, where you see a Stokes drift profile that grows in the course of 4 hours.
I'm not sure if I'm on the
yeah,
right
we're using
slide,
quite a
Annika.
small grid res. Oh,
You on slide 4?
did you get my updated presentation?
I did not
Because
get
I
the
sent you an
updated.
update earlier today.
I didn't. Yeah, sorry, I didn't receive that.
Oh,
So I think I might have an old presentation.
okay. Oh, that's a problem. Oh shit. Let me try share screen then, maybe better.
Okay.
See where it gets us. I go full screen. Can you see my screen?
Yes.
Yeah, we can see it.
Great. Just trying to see how I'm going to get full screen here, but anyway, I'm just going to do it like this. Full screen. We'll find it out later. Okay, so yeah, here we are. Thanks for notifying me that, Greg. So here on the right, you see what the figure I just described. Just a simple sketch of a Stokes drift profile that develops in the course of 4 hours. The grid we're using is quite small, horizontal resolution of 4 meters, vertical 2 meters. So for dynamics that fall within the subgrid, within the scales of that are parameterized using Smugger-Rinsky Lilly closure. Here below is a link to the GitHub where you can find oceanagans.jl for if you're interested in using this or letting some of your students use this in the future. Anyway, to familiarize myself with the package and test out its functionalities, we started working with some idealized simulations, roughly following a publication by Wagner et al. In 2021. I investigated the effect of different types of RC forcing on turbulent fluxes. So we set up an idealized run first, so it's just forced by free convection, even though I'm not presenting results of this. I'm going to focus on the other two idealized cases. The first one that simulates just a wind force ocean surface boundary layer. And the second one, a wind and wave force. So that includes Stokes drift velocities. The table shows some parameters. So both wind and the wind wave case used wind speed of 6 meters a second. That develops in the course of 3 hours. That's this parameter, the period of wind stress growth. There was a slightly destabilizing buoyancy flux, but not very high. And then for the wave case, I simulated Stokes drift for waves or deep water waves with an amplitude of 5 meters. And these waves developed over the course of 5 hours. For all these simulations, I've used so far only a small grid just to make it quick to run on my laptop. Small grid with an extent of roughly 130 meters in the horizontal and 60 meters in the vertical. And as I said, a resolution of 4 meters horizontal and 2 meters vertical. Each of the models is initialized by a 17-hour spin-up to create a weakly turbulent surface boundary layer. And then each simulation, the real simulations themselves with the wind and wave forcing, takes 17 hours each. To start doing some analysis, I sort of inject a tracer and Lagrangian particles into the model at the surface after 9 hours of simulation time. These vertical profiles, I summarize the result of the idealized simulations. The dashed lines represent in each of the panels represent the case where wind was the dominant surface forcing, whereas solid lines present the case where wind and waves were used. Blue lines in the first 3 panels represent U velocity components, red are the V components, and the green in the relevant in some of the panels are the vertical components. The most important differences between the wind only and the wind and wave force simulations are that when Stokes drift is included, the model output suggests that the vertical momentum fluxes, seen in the middle, the second panel here, are larger within the mixed layer, and also that the turbulent kinetic energy component, the vertical component, is way more significant when you include Stokes drift into the model at a cost of the horizontal component, kinetic energy. The fourth panel here shows buoyancy profile, which is the depth integrated version of stratification. It's a simple way to simplify the modeling of density profile. For the idealized cases, I used a deep mixed layer of like 25 to 30 meters above like a stable stratification. The fifth panel here illustrates that for the case of wind and wave force model, that the vertical buoyancy flux is a lot larger than when not including the Stokes drift, and you see that for this third idealized model, you see that indeed some mixed layer deepening is occurring. Well, after having gained a bit of experience with the package and its different components, it was time to set up a simulation that's a bit more specific for the T-Rex experiments. I spent some time analyzing the observations made during the first of the surface experiments in 2020. From this, I quickly concluded that to better represent the study site, we need to make quite a few changes to the idealized case. To mention only a few things, observed that in the area, the surface mixed layer is only 10 to 12 meters deep, and it sits above a stronger stratification than used in the idealized models. Another clear difference is the presence of a sheared background current, both everywhere in the estuary. And third, also the default runs, they were we noticed that they were quite the resolved velocity field was strongly affected by planetary rotation through the inclusion of the Coriolis parameter in the equations. But this may not be all that relevant to the estuarine circulation. So a quick harmonic analysis of the currents observed in the middle of the estuary from an ADCP. They show indeed that the semidiurnal tidal component and its first harmonic cause most of the temporal variability in the currents, and that the inertial oscillations are not the dominant feature in this area. To further illustrate the stratification, which I already mentioned, on the left are shown some CTD profiles made from the small Boston whaler boat, which followed a dye patch released in the 2020 experiment. Here in the middle, you see the track of this boat, and sort of the in the color scheme shows where it shows the dye concentrations measured with a flow-through CTD. The CTD profiles are taken where at the triangles here. So what this shows is two things. Indeed, the stratification is as I said, the mixed layer is quite shallow, and density stratification is stronger than what I had in the idealized case. But also there's quite a bit of spatial variability from what is, I presume, closer to shore to further out into the estuary in the density profiles. Here on the right, you see rhodamine profiles obtained with the same locations from the CTD, which shows that during this dye release, the dye tracer was contained within this mixed layer above 10 meters. And that the vertical gradient remained for quite a few hours to eventually disappear, at least from what was measurable from the boat.
Sorry, Annika, 1 minute if you.
Okay, we're going to skip this because I
possible.
already mentioned that the sheared currents from the ADCP. So yeah, taking in all these observations, as well as records of wind and wave forcing from the central mooring, the following steps were taken to build a more case-specific simulation. So the first more realistic setup uses a stronger stratification. It uses slightly less wave forcing because that's what the observed record shows. It shows a stabilizing heat flux. I think that's the most, but still, this is still quite idealized because we're using these as constant forcings, whereas a second step would be to make these forcings more time variant. The first, some model output using the constant forcing shown in this plot here. What you see is that after about, here after 10 hours of simulation, we do seem to get some structural features in the turbulent or turbulent field as well as in vertical velocity field, which could be interpreted as maybe rotating cells, lung circulations. On the bottom of the visualization of the passive tracer that I use in the model, which also shows some variability in both vertical and the horizontal, but it does remain trapped within this mixed layer depth. Then quickly to the second more realistic setup, we're using time variable simulation. This video, I hope it works. We see that when using time variable simulation, it's going to come quite precise on when to start looking at a passive tracer, because here we see that it takes a bit more time to establish structural features within the velocity field. So this will definitely need a bit more work to get this right and represent the conditions encountered during the experiments. So to conclude, this tryout with Oceanic and SubGL has potential to simulate detailed dynamics related to tracer and particle dispersion. As I have a little bit of time left in this project, I'd like to increase the domain size soon to have a better opportunity to look at horizontal dispersion. I think the vertical we've been focusing on for now the most, and we should have a look at more horizontal dispersion. And yeah, to make some more changes to make this model represent a little bit more the conditions encountered during TRX. There's some work left to do. I'm keen to discuss this with other people involved in the project. Thank you for listening. So if you have any questions or suggestions, let me know now, or we can speak after the session.
Thank you very much, Annika. That was great. In the interest of time, I would like to set the questions in the chat, and then Annika, maybe you could address them as they come in. I believe there's one there already.
Yeah, that's good.
And we can move on. But no, that was great. Thank you very much.
Okay.
And thanks for making the effort from the Celtic Explorer. It's appreciated.
Yeah. Thank you. No problem.
Great. So thanks, Annika. And we'll move on to our next speaker, Taylor Davies, who's speaking to us about using drifters to understand the dynamics of the Labrador current system over the shelf. So Taylor, if you're ready to share your screen, please go ahead. And if you're not unmuted, then please remember to unmute.
Good. Can everyone hear me?
Yes, Taylor, we can hear you.
Okay, beautiful. So I'm Taylor. I'm a master's student at Dow, and I'm supervised by Dr. Eric Oliver. And so far, I've been working with data sets of ocean drifters with the goal of developing a better understanding of the dynamics of the Labrador current system over the shelf. And today, the focus of this presentation is going to be about the methods and some preliminary results for getting tides from drifters. So a little bit of background on our area of study. So the Labrador Sea is a very dynamically important part of the ocean. It's a site of deep convection, so it's a key part in the Atlantic meridional overturning circulation. The Labrador Sea is the gateway between the North Atlantic and the Canadian Arctic. Additionally, the Labrador Current, being the western boundary current of the subpolar gyre, plays a really key role in the export of fresh water and sea ice from the Arctic. Across the shelf, there are two branches of the Labrador Current. There's the inshore branch and the main branch, the inshore being the fresher and weaker counterpart to the saltier and stronger main branch. As we know, climate change is affecting the North Atlantic at really unprecedented rates. So developing a better understanding of the dynamics of the region can be really important and valuable for improving models. So this is very valuable in the context of climate change. So ocean drifters are these instruments that you can throw in the ocean and they drift around recording position and time. So they offer a very unique Lagrangian perspective of fluid flow in the ocean. They can also capture things like boundary currents, tides, as well as inertial oscillations and eddies. But there are some difficulties that arise from the non-stationary frame of reference of these drifters as they're moving in space and time. And that is going to be a focus of the presentation, the methods by which we get around this. So this plot on the bottom here are the current locations of drifters that are a part of something called the Global Drifter Program. So this is part of NOAA's Global Ocean Observing System. And as you can see, the coverage varies a lot depending on your location. So these two maps here show our region of study with two different drifter data sets showing the trajectories. So on the left here, these are drifters from the Global Drifter Program. And as you can see, there is pretty good coverage in the interior of the Labrador Sea. But as you move closer to the coast, you can see that the data becomes much more sparse. So that's obviously a problem for us since we want to look at the dynamics across the shelf. So this plot on the right here are drifters from the CONOC project, which is the community-based observing of Nunatsiavut Coastal Ocean Circulation Project. So these drifters are deployed by community members and local scientists much closer to the coast. So they act to fill that data gap for us. So using these drifters, we want to examine the dynamics of the Labrador current system across the shelf. So what we want to do is break down these drifter velocities, which we get because the drifters record lat, lon, and time, into a time series of physically meaningful signals. So the first step in doing that is to pull out the tides. So decompose the total velocity into a time series of tidal velocity and non-tidal velocity. So this resulting non-tidal velocity could, in principle, be further decomposed into components like the geostrophic flow, Ekman flow, inertial oscillations. But today we're going to concentrate on the method by which we pull out the tides. So some background here on power spectra. So tides are oscillatory, and they can be expressed as the sum of sinusoids of different frequencies. And these frequencies corresponding to those of the different tidal constituents. So for example, M2 or S2. Discrete Fourier transforms will transform a time series, say f of t, from the time domain to the frequency domain. So this plot up on the right here shows the time series f of t. This is actually u velocity from one segment of one drifter. And if we do a discrete Fourier transform on this, we get this plot down here, which is a power spectra. So in the frequency domain, we see that the dominant frequencies of this time series show up as spikes or spectral peaks. So here, there's a peak at 2 cycles per day. So this makes sense in the context of this data set because the dominant tides in that area are semi-diurnal or twice per day. So just as we can take a Fourier transform to go from the time domain to the frequency domain, we can go from the frequency domain back to the time domain with an inverse Fourier transform. So if we pull out these tidal peaks, do an inverse Fourier transform, we can get a time series of tidal velocity. And this is the backbone of the method that we use to pull out the tides. So rotary spectra, we can express u as a complex velocity in this case. And it's very, very similar to the discrete Fourier transform that I just talked about. So this allows us to sort of dig one layer deeper of complexity and get the direction of rotation. So whether it's clockwise or counterclockwise. So here we can see that in this case, at the semi-diurnal frequency, it's predominantly clockwise with not much energy in the counterclockwise. So drifters are moving in space, and this is a problem because they go through different tidal regimes. So if we consider this example, let's say we're looking down at the ocean in the XY plane, and we have a case where the tides are stronger in the south and weaker in the north, indicated by these larger back and forth arrows and smaller ones here. So let's say for case A, we have a stationary mooring. So this is going to be measuring the same tidal regime, and you can see that in this plot here. Case B, we have a drifter moving north from a region of stronger tides to a region of weaker tides. So this is a non-stationary tide, and that poses a problem for our analysis. So what we want to do, or what we decide to do, is consider the tides to be stationary within a small time window. So we can divide up our time series of velocity into a bunch of different overlapping segments and consider them to be stationary within those segments. So how do we choose the length of these time windows? So up here, you'll see two tables which show optimal segment lengths for a diurnal tide and optimal segments for a semi-diurnal tide. So for each thing, so the diurnal or semi-diurnal tide that we want to pull out of this time series, we could have a different segment length. And the criteria for these segment lengths is that we want as close to an integer number of diurnal or semi-diurnal cycles in a given segment. And we define these diurnal and semi-diurnal frequencies by averaging the main tidal constituents in that area. So another criteria that we have for these segment lengths is that we need to have a different number of inertial oscillation cycles in a segment. And that's going to be different from the diurnal and semi-diurnal. So the reason we do that is because we don't want to mix up other oscillatory motions like inertial oscillations with the tides. And this method was sort of inspired following Crawford et al. 1998. So now that we have stationary segments, we can get a full time series of tidal and non-tidal velocities. So this is an example of one drifter for a total tidal and non-tidal time series, but we can abstract this to the whole data set by doing some gridding and bin averaging. So the plot on the left here shows tidal speeds. And as you can see, there are strong tides at the northern tip of Labrador and in the Strait of Belle Isle. So now is probably a good time to say that quality control of this data set is something that we need to do in our future work. Sometimes these drifters capture things that are not in any way representative of ocean currents in the area. And that's evident in this plot here on the left with this really, really strong supposedly tidal signals kind of stretching over here to the tip of Yarmouth. And what actually happened here was a fisherman picked up a drifter in his boat, lugged it aboard, and drove all the way to Yarmouth. So clearly that is not an accurate representation of the ocean currents, but other things can also happen, like it might get lodged on a little sand sill or sometimes come into contact directly with the coast itself. But putting that aside for the moment, we can also examine the ratio of diurnal to semi-diurnal tide. And as you can see from this plot here, in the region, it is predominantly a semi-diurnal tide. We can also look at the semi-diurnal ratio of clockwise to counterclockwise. And as you can see, it is predominantly clockwise. And these findings are consistent with the literature. So looking at the non-tidal velocity, there's a clear distinction of the two branches of the Labrador Current, with the velocities matching up to those within the literature. So about 0.5 meters per second for the main branch and around 0.2 meters per second for the inshore branch. And again, quality control of this data set is something we want to do as shown here by these super, super, super fast velocities of the fishing vessel driving straight to the tip of Yarmouth. So some of the future work that we want to do includes quality control of the data set, as well as incorporating the Global Drifter Program data set into our analysis, and further decomposing the drifter velocity, looking more at that non-tidal component. So for example, like geostrophic flow, equine flow, as well as inertial oscillations. Another thing we want to do is look at connectivity between the inshore and main branch. Thank you so much for listening, and I would love to take questions if there is time.
Great, thank you very much, Taylor. Any questions?
I have just one kind of question comment about, have you looked into any of these like inverse tidal models, like the Oregon State one or the FES, to sort of test this kind of stationarity of estimating the tidal component?
No, we haven't looked at any of it yet, but that would probably be a good thing to look at.
Yeah, I'm not sure how good they are with the currents. The heights are quite accurate.
Okay, yeah, that's something I will write down to look into. Thank you.
Thanks, Greg. And Dave Greenberg, I think.
Hi, yes, just wondering whether the residual current, the non-tidal signal, was tested to see how much energy was left in the tidal bands.
Yeah, that's a great question. We did do some analysis of that, like just doing the Fourier, like the rotary spectra on the non-tidal component. There was some small amounts of tidal energy left in the tidal bands, and we're thinking of maybe dealing with that by like doing another pass of this method on the non-tidal stuff. But I guess the issue with that is the segments will become shorter with each pass. Like you'll lose like essentially a full window length. So it's kind of a balance between like how much of the data set we want to conserve versus like how exact we want to be, if that makes sense.
Yeah, I think, yeah, it does get tricky as you get further and further residuals. It just, even on the full data set, it might tell you something. Thank you.
Thanks.
All right, thank you, Taylor. I think in the interest of time, we'll move on to the next talk. But Taylor, there is a question for you in the chat. So if you want to take a moment to answer Fred's question, that would be really helpful.
All right, thank you very much. And I get the pleasure of introducing the last speaker. So it's Nancy Soontians, and she'll be talking about the impact of ocean model resolution on the accuracy of drift prediction. So whenever you're ready, Nancy.
Thanks, Greg. Slideshow. Okay. Can everyone see the screen?
Yes, it looks good to me.
Okay, thanks so much. Yeah, so I'll be speaking to the impact of ocean model resolution on the accuracy of drift predictions, and this is work that has been conducted at the Fisheries and Oceans Canada in collaboration with Jennifer Holden. But there's also a lot of people who have contributed to this project over the years, so I just want to make sure those people are acknowledged as well. All right, so the work that I'm presenting falls under what's called the Improving Drift Prediction and Nearshore Modeling Initiative of the Oceans Protection Plan. And this component has a goal to build a modular drift prediction and verification tool. So the idea is that we are hoping to bring together all available observational drifter data, ocean model outputs, atmospheric model outputs, and drift methodologies to run drift predictions and compare those drift predictions with observations. And we're aiming to produce a standardized set of verification and evaluation metrics. And then we are hoping to, and what I'll speak to today, is to analyze those evaluation metrics so that we can ask questions about what is impacting the accuracy of a drift prediction given an ocean model, and in particular drift prediction. All right, so the example that I'll go through today is a set of drift evaluations that were conducted in the Atlantic Ocean. So this is actually a really nice segue from Taylor's talk, where she spoke to the surface velocity program drifters, SVP drifters out of the Global Drifter program. So we took those drifters that were available to us in the domain shown here, which is a part of the Northwest Atlantic. We took the drifter data from 2016, and we ended up with 144 drift tracks. And if you remember the picture that Taylor had shown us, these drifters are drogued at, they have a very long drogue that's centered at about 15 meters depth. And the drogue is about 10 meters in length. So the idea behind these drifters is that they're designed to sample the near-ish mixed layer ocean currents with limited impact from the winds. And so given those 144 drifter tracks, we produce modeled equivalent. So the idea is that we release along a single observed drifter track, we released a modeled equivalent every 24 hours. We allow them to propagate for a period of 240 hours or 10 days. And so all in all, we end up with about 9,000 model drifter releases. And the drifters are not, they were only influenced by ocean model current. So we did not include any effects of the winds, because again, these drifters were designed in particular to limit the influence of the winds, so long as the drogue is still attached. And the drift methodology that we're using to support this work is called OpenDrift, which is an open source Python package for generating drift predictions. All right, so the ocean models that we are evaluating under this framework are models that have been developed out of the Concepts program, which is a interdepartmental program within the Government of Canada to produce coupled ocean prediction systems. So the three models that we're looking at are a global scale model called GEOPS, which is a 1/4 degree resolution in the horizontal. We're also looking at a regional scale model called REOPS, which is 1/12 degree model. And then finally, we compare the results to a coastal prediction system called CEOPS East, which is 136 degree. So again, we're trying to answer or look at the question of how did the varying levels of resolution impact the accuracy of drift predictions using the ocean currents from these models. Right. So here's just an example of what we're trying to do. So this is one particular drifter out of the 144 tracks that I had shown you earlier. So this drifter starts on the Newfoundland shelf, actually right at the shelf edge. The observed drifter trajectory is shown in black, and then I've shown also all the model releases in the different colors. So GEOPS is in green, REOPS is in red, and CEOPS East is in blue. So again, along that black track, we release a model drifter every 24 hours, and the drifters are allowed to are simulated for a period of 10 days each. And so in this particular example, you can see the observed drifter follows along the shelf edge. It goes through Flemish Pass, comes around the tail of the Grand Banks, and then is eventually pulled into the large meandering North Atlantic current. And the modeled trajectories do something similar, although there are quite large discrepancies between what's happening in the models and in the observations, and in particular, the largest distances, just by eye in this plot, happen in that sort of meandering part of the flow. And that's fairly consistent across each of those different models. All right, so how do we go about evaluating these predictions? So we've looked at a few different metrics, and the few that I'll show today or discuss today are called the separation distance and the Mulcard skill score. So the separation distance is simply, given an observed and modeled trajectory pair at every point in time in the trajectory length, how far apart are the observed and modeled drifters, right? So that's a simple distance metric. But the challenge with that is that in situations where the flow speed is variable, the separation distance depends on the speed. So in fast-moving flows, you can expect that that separation between the observed and model drifter pairs is higher, and in slower flows, you could expect that it's smaller. And so a way to get around that is to try to normalize the separation distance. And you can use a metric called the Mocard skill score for that. And so just to demonstrate on the diagram here, the Mocard skill score normalizes the separation distance, which is the small letter d, by the distance that the observed trajectory has, or the displacement of the observed trajectory from its original position. So again, trying to take account that if you're in a high speed environment, the observation is going to travel further, and so that that normalization helps you to compare across different flow regimes. All right, so here's a very quick overview of the results. So again, earlier I showed you one particular drifter example.
Sorry, just to interrupt, Nancy, could you hide the stop sharing? Is that on your side?
I didn't know if you guys could see that or not.
No problem.
Hide. Thanks.
All right, thank you, Nancy.
Yeah. Okay, so for for all the drifter tracks that we had released, we can do some averaging of those skill scores. And so the first plot is on the left, where we show the separation distance, how it evolves over time, with GOPS in green, REOPS in red, COPS east in blue. And I think one thing that stands out is that all the models are indeed very similar when we're averaging over this large data set. But the REOPS model, which is that intermediate resolution model, seems to have, a marginally increased performance. So if you think about it in terms of an average separation rate, GOPS is 15.1 kilometers per day, REOPS would be 14.3, and COPS east was 15.2. Okay, and you get a similar scenario with the Mocard skill score. So with that Mocard score, a value of 0 would indicate very low skill, and a value of 1 would indicate perfect skill. And with this metric, we're also seeing that the REOPS model seems to have slightly improved performance over the GOPS and COPS east, which was a bit of a puzzle, right? Because when we're thinking about our ocean models, one of the reasons that we go to these higher resolutions is to have a more accurate representation of the processes and currents that we're trying to represent. But that doesn't seem to be the case for this comparison. So that's where we started to look into this idea of unconstrained scales and spatial filtering. So one thing I didn't mention is that GOPS and REOPS both have some kind of data assimilation. So they take in observational data and sort of nudge or correct the model to be more like the observations. But COPS east doesn't have that, although it does have some what's called spectral nudging. So in a certain region of the domain, the COPS east model is nudged towards REOPS, and that's the sort of region that's off of the shelf, where I have to define the shelf by I think it's the 1500 meter isobath. Okay. So this question of unconstrained scales, where those currents and COPS east aren't really constrained by any physical observations, it might explain why it seems to have a lower performance. So we thought about maybe filtering the ocean currents before running these drift predictions, and the reasoning behind that is that if maybe an eddy in the COPS east model is in a slightly wrong place, that could really impact the results of a drift prediction, because the errors in a drift prediction accumulate rapidly over time. And so if there's one thing that's off, it's going to have an impact later on in the prediction. So we considered these spatial filtering at 3 different length scales. So we're basically just averaging the currents over a box of 25 kilometers, 50 kilometers, and 75 kilometers around each grid cell. And here's just a quick snapshot of how that filtering impacts the surface current for, actually it's not surface current, it's 15 meter current for this point in time. All right, so what happens when we apply the spatial filtering on the COPS east results? So here we have those different length scales of the filtering and different colors of blue. with the biggest filter, 75 kilometer filter, in the lightest blue, and so we see a slight improvement in the average separation rate at 14.2 kilometers per day, compared to without the filtering was 15.2 kilometers per day, and that's a little bit better than REOPS, although there's a lot of variability, as you can see by these are the dotted lines are the interquartile range, so there's a lot of variability around those averages. And so I did want to speak to what's happening with the filtering. What is the impact of doing that filtering? So again, if I go back to that example drifter that I showed earlier, and take the along that observed drifter track, we can calculate things like the eastward and northward velocity of that drifter, and that's shown over here on the right in the black time series line. But we can also do the same thing for the model output. So in blue is that original COPS east, and in orange is the highest or the largest filter, 75 kilometer filter. And I think one thing that stands out to me is that by doing that filtering, we are reducing the variability at the shortest time scales. But the sort of larger time scale or larger scale variability has not been reduced. And so to me, what that speaks to is that when we're looking at drift prediction and ocean models, if your prediction is a little bit off early on, then that's going to have an accumulation of errors. But by doing this filtering, it seems like we're sort of reducing the sort of energy at these higher frequencies, and so that the amount that your current is off might be a little bit less. So we can take a
1 minute, Nancy.
Okay, yeah, thanks, Greg. This is the last slide, just a quick, I guess, summary of what I had just discussed, but looking at the power spectral density or the rotary spectra for the negative and positive frequencies. And you see where we're at the lower frequencies, I guess the sort of difference in the power spectral density between the lowest and highest frequencies, and that orange curve is very, very large compared to the blue and the black curves. Okay, all right, so just a quick summary. We are building a modular tool for characterizing and evaluating drift prediction ocean models. There's this sort of, we've noticed a funny situation where a higher resolution model didn't seem to perform the best, and that might be explained by the fact that those higher resolution models don't always have, like, some of the scales are just unconstrained. And I just wanted to mention that that's not always the case. So in some of our studies, we have looked at high resolution models in very coastal areas where the dynamics are constrained by things like the bathymetry and the coastlines. And in those cases, we do tend to see that the higher resolution model usually gives some improvement. So this speaks to this idea of filtering or pre-treating ocean model outputs before being used in a drift prediction. And then finally, there's more work that's needed to understand the uncertainty in these ocean model fields and how do you account for that when you are running a drift prediction. Okay, that's everything. Thanks.
Thank you so much, Nancy. That was great. I see we have a question from Manny Madinia. Would you like to ask your question? Oh. Can't hear you.
Can you hear me now?
It's very quiet on my end. Can you hear Nancy?
Can you hear me?
I can barely hear.
How about now? Is it better?
Oh,
there,
that's good.
yeah, much better.
All right, I'm sorry. I have actually 3 questions, and I would be appreciative if you could answer those. That'd be great.
Not here. The Drew is too low, the voice.
Yeah, it's still a bit quiet.
Can you hear me?
Yeah, just
put it
if you
in
could
chat.
speak up.
I just put it in chat. Just use that.
Oh, okay.
Okay. You see the question, Nancy?
So, okay,
So I can read it out if you like. It says,
okay.
why use distance between endpoints in Molcart? Wouldn't using actual distance travel better and more meaningful, for example, for a vortex? So yeah, the integrated path. Also, filtering reops results does not show results that are very much better than COPS. Why do you think this is? Also, why not do temporal averaging? You only do spatial averaging.
Yeah, those are great questions. So first off, for Molcart, it's just one of the skill scores that is available. So there's lots of different options. You're absolutely right that you could do more like an integrated distance, and in fact, that's one of another set of metrics that we have produced. But I just didn't speak to that today. So there's a paper, Liu and Weisberg, who speaks to a different type of metric. So for the filtering, aren't very much better. I didn't filter reops, so just to be clear, I was only applying the filtering to that higher resolution model COPS. And yes, again, I think that's a really interesting question: is why isn't there really much improvement? I think that part of that could be just the challenge of drift prediction. It's a very, very difficult problem to do correctly. And so I think that's what these results are speaking to, that it's just a really challenging way to evaluate an ocean model. And why not temporal averaging? Yeah, and that's another aspect that could be explored and has indeed been explored. I don't have any results to speak to that today, but looking at temporal averages is also something that we've considered. Hope that answers your question.
That's great. And Jinyu Sheng has a question. He has his hands up. I think he will ask it.
Yeah.
Jinyu, you there? Yeah.
So yeah. Hi, Nancy. So kind of an interesting talk. So I want to know, the three different models have a different horizontal resolution. Is the same external forcing? Is the same forcing used in the three model?
No, that's a good point. The forcing is not the same between the three models. Yeah.
Yeah, and also the horizontal mixing, vertical mixing could be also different in the different resolution too, I think, isn't
That's
it?
correct. Yeah.
So I'd like to know how is the general circulation over Eastern Canadian shore? Over Eastern Canadian shore is produced by three different models. So in theory, the final resolution should do a better job, right? And in simulating 3D circulation.
Mm-hmm. Yeah. So
as
another important component would be the forcing fields that go into those higher resolution models, and those are different. And I know the forcing fields are typically higher resolution themselves.
So when you do the particle tracking, did you consider random walk? Because there are some small scale process not resolved by the circulation model. So you don't include random walk in your particle tracking?
Right, not in this example. And it's again, I think, another important question when comparing across different resolutions, like what would that appropriate random walk value be for the different resolutions?
Yeah.
So in this case, no, that was not not a parameter that we played with.
Okay, thanks, Nancy.
More questions. 10-day, or these really forecasts. So Danny or Drew, I guess, though there was not using the forecast from GOPS, COPS, and REOPS. These were, like I said, I guess hindcasts or historical runs. So there were no forecast outputs used in those predictions. Yes, I think that the ensemble approach would be also something really interesting to consider. And Amina, windage factors. No, we did not use any windage factors for these drifters. As I mentioned, these drifters were designed to have very limited influence by the wind field. And so we did not use windage in the simulations.
Okay. Thank you very much, Nancy. I think it's a good spot to wrap it up. So thank you everyone for attending our session, and all our speakers doing an excellent job. There will be part 2 of this session in a couple of hours. So I'll have time to get some food. So yeah, thanks again, and hope to see you all there.